Okay, so we're going to move on to Chapter 4 now, and Chapter 4 is all about the graphs of the trig functions. So what I want to talk about today are the graphs of sine and cosine. And you may be familiar with these already, but then this may be new information for some of you. So let's talk about the graphs of sine and cosine. So this is 4.1. Graphs of sine and cosine. And we'll also talk about the other trig functions as well a little bit later. Let's talk about the graphs of sine and cosine. So to begin with, let's start off by graphing f of x equals sine x. And again, several of you may already have a good idea about what this thing looks like, but I'm going to run off of the assumption that you've never seen this before, and so we don't really have any intuition about what to expect this graph to look like. So what I'll do is make a table of values. And we'll just plug in a bunch of angles for x and see what the corresponding outputs are. So we should choose the angles wisely so that we have a good idea of what the values are. So if we plug in 0 for x, sine of 0 is 0. Another good value would be like pi over 6. If we plug in pi over 6 for x, sine of pi over 6 is 1/2. If we plug in pi over 4, sine of pi over 4 is root 2 over 2. And for the purposes of graphing, we might want to know about how much that is. I think that's about 0.7. Okay, pi over 3 is going to put us at root 3 over 2. Root 3 over 2 is about 0.9. And then finally, by the time we get to pi over 2, sine of pi over 2 is 1. Okay, and we can kind of continue on in that way and kind of go around the entire unit circle. Let's start plotting these things though. Actually, let me just go a little further. So I think I'm gonna plot, maybe instead of doing pi over 6 and pi over 3, I'll just go pi over 4. So the next one I'll go to is maybe 3 pi over 4. Well, 3 pi over 4 is the same, sine of 3 pi over 4 is the same as sine of pi over 4, right? So that's about 0.7. And then we make it all the way to pi. Sine of pi is 0. After that we would go, right, pi is 4 pi over 4, so then we would make it to 5 pi over 4. That puts us in quadrant 3 though. Sine is negative there. So, so it's going to be the same value as 3 pi over 4, but negative. So this is about negative 0.7. Then we make it to 3 pi over 2. At 3 pi over 2, sine is negative 1. And then we would get to 7 pi over 4, and we'd be back at about negative 0.7. And then finally we'd get back to 2 pi, and that puts us back to where we started. Okay, so as you can see, the values, they always remain between negative 1 at the lowest and positive 1 at the highest. So I'm going to mark on here, let's say pi over 2, pi, 3 pi over 2, and 2 pi. And we can put 1 and negative 1 on there. And then we can plot some points, right? So we know that at 0, y is 0. When x is pi over 2, y is 1. When x is pi, y is 0. When x is 3 pi over 2, y is negative 1. And when x is 2 pi, well, then we end up back at 0. So we get this kind of shape, but we don't technically know if these are like sharp corners or what they do exactly until we come back and fill in some of these details, right? So at pi over 4, for example, I know that I'm at 0.7, so that's maybe right about there. And then the same thing at 3 pi over 4. At 5 pi over 4, I'm at negative 0.7. So maybe something like this. And we could go back and fill in the pi over 6 and the pi over 3 as well. Pi over 6, we're at 1/2. At pi over 3, we're at 0.9, so it's looking something like that. So I don't think that the picture we get are these sharp lines. I think we get this smooth curve that looks kind of like this. Now this is just if we graph between 0 and pi, or sorry, 0 and 2 pi. But of course, we could plug in values bigger than 2 pi. What's going to happen is that this thing is just going to repeat, right? Because it's a periodic function, so it's going to repeat over and over again, and the same thing's going to happen in the other direction. It's going to repeat, right? And so that's the picture that you're going to get for the sine function. So that's what the graph of f of x equals sine x looks like. Okay, so a couple things to point out about this graph. So first of all, it's periodic with period 2 pi. So what that means is that this function just repeats over and over and over again, and the chunk that repeats is 1 period. So in this case, 1 period is 2 pi units long, because that's one segment of the graph, and then it's just copies of that forever and ever in both directions. Okay, so it's periodic with period 2 pi. Okay, it's symmetric about the origin. So if you're a little rusty on your algebra, what it means to be symmetric about the origin is that if you fold the graph in half along the x-axis and then fold it in half again along the y-axis, then the graph will meet up. So imagine just taking this kind of hill here and flipping it over. Now it's a hill going this way, right? And then you flip it over this way and it matches up with this hill right there, or I guess this pit, right? So that's what it means to be symmetric about the origin. Now, if you remember back to your algebra days, symmetry about the origin had a particular name. We called functions that are symmetric about the origin odd functions, right? So therefore, sine is an odd function. Okay? What does that mean? Well, that means that sine of negative x equals negative sine of x for any real number x. Okay? That's not true of all of the trig functions. We'll see in a second that that's not always the case, but it is true for the sine function, which is interesting. Okay? So it's symmetric about the origin. That means that it's an odd function, which means that sine of negative x equals negative sine of x. So this is called the odd identity for sine. All of the trig functions have either an even or an odd identity that we're going to discover throughout the course of this chapter. Okay, what else about this graph? It has domain negative infinity to positive infinity, right? All real numbers. You can plug in any real number to the sine function and get a value back, right? It has domain negative infinity to positive infinity, and range. What's its range? So its range, it ranges between -1, y equals -1, and y equals +1. So its range is -1 to +1. Okay. And then this last one is just kind of, in case you see it in the book or whatever, but its shape is called a sine wave or a sinusoid. Right? So, so that kind of wavy shape is called a sinusoid. It's called it's a sinusoidal wave. Okay, so that's the sine function, right? That's what it looks like. Let's graph the cosine function now, and we'll go through this one maybe a little more quickly now that we've done the sine function. You can kind of suspect that we're going to have a smooth curve, and it's going to be kind of like a wavy kind of function. So I'm not going to plot as many points. I think what I'm going to plot are just the quadrantal angles. So I'll start 0, and then I'll do pi over 2, and then I'll do pi, 3 pi over 2, and then 2 pi. Will get us back to where we started. So those are the points that I'm going to plot for the cosine function. Okay, so now let's think. If I plug in 0 for x to the cosine function, cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is, that puts us back at 1. So let's see what's going on here. So pi over 2, pi, 3 pi over 2, and 2 pi. Right? 1, -1. And what do we have? So this time we're starting up here at 0, 1. Then we go down to pi over 2, 0. And then pi -1. And then 3 pi over 2, 0. And then 2 pi, 1. So it's looking kind of like this. Okay. Now, just like with the sine function, we can plug in bigger and bigger values, right? So this thing we know is going to really keep going forever and ever in this direction. And same thing in the negative direction, right? So it's going to keep going forever and ever, kind of like this. Okay, so this is what the cosine function looks like. Really similar to the sine function. In fact, if you take this function and just shift it to the right, pi over 2 units, you get the sine function, right? So imagine taking this graph and just shifting it over pi over 2 units. Then this point ends up there, 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 and so forth. And you just get exactly the sine function, which is where we get one of those identities, right? One of the cofunction identities. That's what the name is. That's where we get the cofunction identities from. Okay. But here's something that I'll point out about the cosine function. So this function is also periodic with period 2 pi, right? This is the snippet of the function that just repeats. It's just a copy of this thing over and over and over again, right? So it's periodic with period 2 pi. It's not symmetric about the origin, though. This one is symmetric about the y-axis, right? Why am I having a hard time writing this word today? Symmetric about the y-axis. And if you remember back to your algebra days, you think back, what does that mean? If it's symmetric about, well, first of all, graphically, that means that if you fold this across the y-axis, the two halves meet up, right? And you can see that. So just imagine this little half of the hill, and imagine folding it across the y-axis. Well, it's going to meet up with this half of the hill, right? And same thing for the rest of the function. So it's symmetric about the y-axis, but that means that cosine is an even function. And the fact that it's an even function tells us that cosine of -x equals cosine x. Okay, so unlike the sine function where sine of -x equals negative sine of x, cosine -x just equals positive cosine x, right? Because cosine is even, right? So these are the even-odd identities. But anyway, just like the sine function, this has domain negative infinity to positive infinity. It has range -1 to 1, and it's also called a sinusoidal wave, right? So it's got its shape is called sinusoidal. I want to show you an animation in excuse me, in Desmos that I think is kind of cool, and it could help you maybe to understand a little bit here. So what we've got here in Desmos is we've got the unit circle, and I'm going to press play on this little slider, but Desmos is going to sketch out the sine function, right? So the sine function is in green. Right? So keep in mind that sine goes with your y value, so your y value is increasing and then decreasing, and then they decrease so much they get negative, right? Start to increase again until they become positive, and so forth. So this is what the unit circle looks like, but then this is how sine gets sketched out, I guess over time, you might say. So that's the sine function. Now here's the cosine function. So the cosine function goes with your x values. So let me start that again, right? The cosine function on the unit circle goes with the x coordinates of the points on the unit circle. That's what I meant. That's what I mean when I say that cosine function goes with your x values, right? So here you're starting when x is its largest, and then as you move around the unit circle, x is going to get smaller and smaller, so that the output starts at its maximum and then it gets smaller and smaller, right? So that's what the cosine function looks like. So another sinusoid, but anyway, it's kind of cool. I could watch it all day. But there you go. So hopefully that makes some sense to you, and you understand a little bit about those functions. If you didn't know what their graphs looked like before, well, now hopefully you do. Okay. So as far as graphing these things go, obviously we're not going to just sit around and graph like sine x, cosine x all day. We're going to want to graph transformations of those things. So we're going to want to be able to graph things like sine of 2x or -3 cosine of 1/2 x, right? Things like that. So what I want to point out to you as far as graphing those things are concerned, and we saw this when we graphed the cosine function together, is that we can get a pretty good picture of the sine and cosine functions just by graphing the quadrantal angles 0, pi over 2, pi, 3 pi over 2, and 2 pi. Just by plotting those 5 points, that gives us the maximum values, the minimum values, as well as the x-intercepts of the graph. Now, these 5 points split this interval into 4 equal parts. Okay, so when you're dealing with just like sine x, cosine x, where the period is 2 pi, then you want to split 2 pi into 4 equal parts in order to find these 5 points. If the period is different than 2 pi, we're still going to split the period into 4 equal parts, whatever the period is. So let's say you're dealing with a function and the period, instead of being 2 pi, is like 3 pi over 2. Well, we would still divide 3 pi over 2 into 4 equal parts in order to find these 5 special points. Okay? And I'm going to refer to these as the 5 special points. So when I give you a problem on a test or a quiz and I say, graph this function, make sure to plot the 5 special points, these are the points that I'm talking about, right? Or transformations of them, okay? Which we'll see by looking at a few examples. So let me give you some examples now, so you can see what it is I'm talking about. So we're going to graph a few things. Let's graph f of x equals sine of 2x. Okay, so first of all, to find the period of this function, we know that the argument here For the sine function, the sort of parent function sine x, the period is 2 pi. So we would trap this argument between 0 and 2 pi. So I'm going to do the same thing here. I'm going to trap this argument, 2x, I'm going to trap it between 0 and 2 pi, since the period of the original parent function is 2 pi units. Now I can solve for x by dividing through by 2, right? So if I divide through by 2, we get 0 is less than or equal to x, which is less than or equal to pi. So that tells me that the period of this function is actually pi, right? So the period of the parent function is 2 pi, but the period of sine 2x is just pi. It's 1 pi, right? Okay, so now I want to divide that into 4 equal parts so that I can find my maximum and minimum values as well as my intercepts and everything. So, so if I take the period, so my period is pi minus 0, right? Pi minus 0, which is pi. And then I take that and divide it by 4. So pi divided by 4. That tells me how much I need to add starting at my starting point here in order to get the next point in that sequence of 5 points, right? So the points that I want to plot are going to be 0, and then 0 plus pi over 4, and then pi over 4 plus pi over 4, which is 2 pi over 4, or in other words pi over 2, and then 2 pi over 4 plus pi over 4, and then 3 pi over 4 plus pi over 4. Right, that's 4 pi over 4, or just pi. So those are the points that I want to plot. So what I'm going to do is make a table of values now with those points. Okay, that'll give me one period of the graph. And I can plug these into the original function to see what the function values are, right? 2 times 0 is 0, sine of 0 is 0. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. 2 times pi over 2 is pi. Sine of pi is 0. 3 pi over 4 times 2 is 3 pi over 2. Sine of 3 pi over 2 is negative 1. And then pi times 2 is 2 pi. Sine of 2 pi is 0 again. So this is the graph that I end up with. So make sure to label your axes appropriately. The labels are really everything when it comes to graphing trig functions. Okay? Because the shape doesn't really change, right? It's just the labels that end up changing. So that's one period of the sine function. This thing, of course, is going to go on and on forever. But there's one period. Okay? Now, I'm not always going to show all of this detail. For example, let's do another one together. Let's do cosine 3x. Okay, so first of all, to find the period, we know that the period of cosine of just 1x is 2 pi. So we're going to trap 3x between 0 and 2 pi, and then solve for x. Okay, so the period is 2 pi over 3. 2 pi over 3 divided by 4. That's the same thing as 2 pi over 3. 2 pi over 3 times 1/4. The 2 will cancel 2 there and leave a 2, so this is pi over 6. So this tells me that I need to add pi over 6. So when I make my little table of values over here, I'm going to start at my starting point 0, but then I'm going to add pi over 6, right, because of this value right here. So I'm going to say I'm going to add pi over 6. And then to get the next value, do pi over 6 plus pi over 6. It's 2 pi over 6, which is pi over 3. And then to get the next point, I'm going to go pi over 3, so 2 pi over 6 plus pi over 6, that's 3 pi over 6. 3 pi over 6 is the same as pi over 2, right? So I'm just adding pi over 6 each time. And then I'm going to do that again. 3 pi over 6 plus pi over 6 is 4 pi over 6. 4 pi over 6 is the same thing as 2 pi over 3. And then I'm going to stop there. And I know to stop at 2 pi over 3 because that was this value right here. Okay, so this value tells you how much to add each time. So you take whatever your period is, you divide it by 4, and then that's the amount that you need to add to get from one point to the next, right? This value is your stopping point. So this is your starting point, your stopping point, and how much to add to get the 3 points in between, okay, the 3 points in the middle. The other thing is that if you memorize the pattern for cosine, then you know for cosine we start at 1, and then we go to 0, and then -1, 0, and 1. And I just have that memorized, right? I just have that pattern memorized. This is the pattern for cosine, this is the pattern for sine. But if you have the pattern for cosine memorized, then you can just write those things down. Now you can check your work if you want. You can plug in 0, you can say 3 times 0 is 0, and cosine of 0 is 1. You can plug in pi over 6. 3 times pi over 6 is 3 pi over 6, it's pi over 2. Cosine of pi over 2 is 0, right? And so you can go through and check them if you want. You could even just plug it into your calculator if you want to check it through your calculator. But there's really no need to even do that if you have these things memorized. So we can plot the points. And then this gives us one copy of the cosine, or one period, I guess I should say, of the cosine function. But of course it's going to continue on and on, right? But that's what that one would look like, all right? So there's f of x equals cosine 3x. So that's typically the way that I'm going to do these problems. Now this process, if it seems like overkill to you to show all of this work, I promise you that the problems are going to get more complicated. Like when we start doing cosine 3x plus 5, or 3x plus pi over 2, you know, minus 7 or something. For things like that, you're going to want to keep track of your work this way. It'll just make things a lot easier. Okay? What you don't want to do is just plug in random points to this function. I want these specific 5 points, right? I want the 5 points that split the period into 4 equal sections, right? And these are the points that do the trick. Okay, so let me give you one more. So I'll let you work on this one. Go ahead and pause the video and see if you can do sine of 2/3 x. Okay, so here's my solution. So first of all, I've got to figure out the period of this thing. So I'm going to squeeze 2/3 x between 0 and 2 pi, and then solve for x. So I should multiply by 3 halves, right? 0 times 3 halves, of course, is just going to be 0. 2 pi times 3 halves is going to be 3 pi. So the period this time is 3 pi. So I need to add 3 pi over 4, right? Since the period is 3 pi, I need to add 3 pi over 4. Starting with my starting point and ending at my ending point. Okay, so let's do it. Starting at 0, I'm going to add 3 pi over 4. Then I'm going to do it again. That'll get me to 6 pi over 4. 6 pi over 4, though, is the same thing as 3 pi over 2. Anyway, then I'm going to do it again. 6 pi over 4 plus 3 pi over 4 is 9 pi over 4. And then I'm going to do it one more time. Remember, you should have 5 of these points. So one more time, 9 pi over 4 plus 3 pi over 4 is 12 pi over 4. 12 pi over 4 is the same thing as 3 pi. Okay. And now this is the sine function. So the sine function starts at 0, then it goes up to 1, comes back down to 0, goes down to -1, and comes back up to 0. So that's the pattern we should have. You're welcome to check it by plugging these values in. But let's graph it. Okay, 0, 1, 0, -1, 0. And there's one period of the sine function. Okay. Now you'll notice that this looks almost identical to what we did for part A. The only difference is the labels. And so that's what I meant when I said earlier that the labels are really everything when it comes to graphing trig functions. The labels are the only thing that makes these two problems any different from one another. So make sure that you're labeling your axes. On a test or a quiz, if you don't label your axes, I'm going to take off points for sure. Probably I'm going to take off most of the points. If I give you this function and all you do is come along and just graph a little sinusoid, I'll give you like 1 out of 5 points, right? The labels are really everything. Okay. So if we multiply the input like we did on the previous problems, then it changes the period. Okay. But what happens if we multiply the output? Well, if we multiply the output, that affects something called the amplitude, right? So the amplitude of a periodic function is half the distance between its maximum and minimum values. So for example, f of x equals sine x has amplitude 1 because the maximum value of the sine function is +1 and the minimum value of the sine function is -1. The distance between +1 and -1 is 2, and so half of that distance is 1, right? So the amplitude is half of the distance. More generally speaking, we can say this. F of x equals a sine x and g of x equals a cosine x both have amplitude absolute value of a. So if a is -3, so for example, f of x equals -3 sine x, that would have amplitude 3. And it would mean the maximum value is +3, the minimum value is -3, right? Same thing for cosine. All right. So to graph these kinds of functions where we're multiplying the output value by something, we just multiply the outputs, multiply all the outputs in the table by that amplitude. Okay. And of course, if the number in front is negative, well then you've got to change the signs as well. Right? So I guess you're not really multiplying by the amplitude, you're multiplying by that coefficient, right? Whether it's negative or positive. So let's practice graphing some things. We'll state the periods and the amplitudes as well. So here we go. Okay, so let's graph, state the period and the amplitude. Let's do this for f of x equals 2 sine x. So a relatively simple one. Okay, there's really no work to be done for the period or anything like that. I mean, we know that the 5 special points are 0, pi over 2, pi, 3 pi over 2, and 2 pi. What changes here is the output, right? Since we're dealing with 2 sine x, that means whatever sine x is, we have to double it, right? So when x is 0, sine x is 0, you double that and you still end up with 0, of course. But at pi over 2, sine of pi over 2 is 1, and 1 times 2 is 2, so you see that gets doubled. At pi, we're back at 0. At 3 pi over 2, we would normally be back down to -1, but because we've multiplied this by 2, we're actually going to go all the way down to -2. And then at 2 pi, we're back to 0. So again, the labels are really everything. The shape is not going to be that different from anything else that we've graphed so far. Okay, but this is what we've got now. Okay, so that's that one. We're supposed to state the period and the amplitude. Well, the period here didn't change because we weren't multiplying the argument by anything, so the period is still just 2 pi. The amplitude, it's this number, or the absolute value of that number anyway, so the amplitude is 2. So the period is 2 pi, the amplitude is 2. Okay, let me give you another example. Let's do f of x equals 3 cosine 2x. So this time we're going to have something that affects the period and the amplitude, right? So let's figure out the period. We're going to squeeze 2x between 0 and 2 pi, and then we'll divide through by 2, so we get 0 is less than or equal to x is less than or equal to pi. So the period is pi. We need to divide the period by 4 to figure out what to add. So we're going to add pi over 4 when we make our table of values. So we're going to start at our starting point 0 and then add pi over 4. And again, and again, and again. Okay? Now, we also need to multiply the outputs by 3, and this is the cosine function, right? Cosine usually starts up at 1, but we're multiplying by 3 now, so we're going to start at 3, and then go down to 0, and then go down to -3, and then go back up to 0, and then end where we started at 3. Okay, so start at 3, down to pi over 4, -3, 0, 3, and that's one copy of the period. Okay, so that's that one, right? That's 3 cosine 2x. The period in this case, what period is pi, and the amplitude is 3. Now, by the way, in case you couldn't tell yet, in case you haven't, in case your intuition is still struggling to catch up, look, the period is going to be, for sine and cosine anyway, sine and cosine usually have a period of 2 pi. So the period of some kind of transformation of that function is going to be, you divide by whatever number you're multiplying x by. Okay? So if the period is normally 2 pi, then in this case the period would be 2 pi divided by 2, which would just be pi. Anyway, same thing goes for these function, right? So we found that this function had a period of 3 pi. Well, yeah, 2 pi divided by 2/3 is 3 pi, right? Anyway, so that's kind of a quick way to tell what your period is going to be. Okay, let me give you one more. This one I'll let you pause the video and kind of work on. See if you can come up with the graph on your own. But give f of x equals -1/2 cosine of 3x. Give that a try. See if you can do that on your own. Okay, so first of all, to find the period, we squeeze 3x between 0 and 2 pi and then solve, right? So x is between 0 and 2 pi over 3. That means that x must have a period of 2 pi, or sorry, f must have a period of 2 pi over 3. Okay. So f has a period of 2 pi over 3. Now, what do we add? We're going to add 2 pi over 3 divided by 4. That's the same thing as multiplying by 1/4. So that's pi over 6. So we saw one kind of like this right, already, but we're going to add pi over 6. So starting from our starting point, 0, then we're going to add pi over 6. And again. And again. And again. And once you've got 5 numbers listed here, you should end up at your stopping point. Okay? It would, in this case, 2 pi over 3. Okay, so we've got those. Now, we've got to also multiply our outputs by -1/2. So for the cosine function, we usually start at 1, but since we're multiplying by -1/2, we're going to have a -1/2 there. Here we would be back to 0. Here we would be at -1, but -1 times -1/2 is +1/2. Here we're at 0, and then here we're back at -1/2 where we started. Okay, so we're starting here and then working up kind of this way. Okay, so that's that one. So that's -1/2 cosine 3x. Period here is 2 pi over 3. And the amplitude is 1/2. Okay. So that's all I have to say about graphs of sine and cosine for now. We're going to do some horizontal and vertical shifting in the next section, in addition to these things that we just got finished doing.